So good morning, everyone. Today I'm going to be talking about some work we did on dynamically reconstructing relocation information for stripped binaries. So let me start by giving you some motivation for our work. As most of you probably already know, address space layout randomization, or ASLR, is one of the most widely deployed and prominent mitigations against code reuse attacks. However, this technique relies on some relocation information in order to be able to randomize the location of its executable module, which is not always available in legacy application, and especially in the Windows ecosystem. So the goal of our work was to try to come up with a technique to reconstruct this missing relocation information in order to enable ASLR for legacy applications. So for the rest of the talk, I'm going to start by giving some more background information on ASLR and relocations. Then I'm going to describe the design and implementation of our technique to reconstruct this information, followed by the evaluation we did, mostly for the performance and the correctness. And finally, I'm going to summarize. So the introduction of the W or execute memory policy prevented most of the code injection attacks. And the attackers, not being able to inject a code anymore when they were gaining the control of an application, they were led to try to reuse some of the existing code. So ASLR was introduced as a technique to mitigate this type of attacks by randomizing the location where code is loaded at runtime, so the attackers wouldn't be able to know where the code is and thus wouldn't be able to reuse it. So as I said before, this is one of the most widely deployed techniques, and it has been proved to be effective and efficient. Now, in Windows, every executable comes with a preferred load address, which is an address that this module would prefer to be loaded at runtime, and this is usually set at compile time. So once a binary is compiled, every memory access within the code uses absolute addresses based on that preferred address. And here's an example. So assuming that the preferred address of an executable module was the 400,000 one, we could see instructions like this one, the jump instruction, using absolute values based on this address. So each of these modules also contains a special section called d.reloc, which lists all the offsets within that binary module that contain absolute address based on that base address. So when the program loader is asked to load any of these modules to a location which is not the preferred one, what we'll do is that it will go through all this list and then fix these absolute addresses within the binary. So when we first started approaching this problem of reconstructing the missing relocation info, we first considered doing so statically, just getting a binary, analyzing it, and then trying to come up with which are the places where there are absolute addresses in order to fix them. However, this would require for us to have a complete and accurate disassembly of all the binary in order to be able to find this info, which is difficult to do in some cases because these stripped binaries, they also lack debug symbols. So it's difficult to get accurate disassembly. So static reconstruction proved to be almost infeasible in most of the cases. We turned our head around and tried to do something at runtime based on monitoring the memory accesses that happen there. And although there are a few different ways of doing this monitoring, we decided to go with page table manipulation, mostly for two reasons: because it provides good performance, I'll see later in the evaluation section, and because we don't have to, to depend on any third-party frameworks like dynamic binary instrumentation toolkits and so on. So here's the basic design of our approach. Given a program, a binary that we want to reconstruct the missing relocation information, we load it, but this time we make the original code location, the .text section, inaccessible, So if control is transferred there, or if anybody tries to read something from there, we get the trap. And then we put the code to a new random location, which is down here in the right picture. So again, whenever the code tries to access something using an absolute address based on the preferred address of this executable module, we will get a trap, and then based on that trap, we will decide what to do. And these decisions are based on this flow graph here, which looks kind of complicated. So I will guide you through the most important parts later on. What's important to see here is that starting from the trap, we have only 3 terminating conditions. So we either successfully verify that we found an absolute address that is relocatable, and then we reconstruct the relocation info for that, or we detect a code reuse attack, or in some cases that I will explain later, we just fix some of the operands and we let the program continue execution. So, as I said before, when an access violation occurs, we receive 2 pieces of information. The first one being the location of the instruction that called this trap, and then the second one being the faulting address itself. Given these 2 pieces of information, there are 2 possible outcomes. These are either the same or different. In case they are different, it means that an instruction caused a trap based on an address, or a different address. This usually means that it's an instruction that's trying to access some memory that is not allowed to. And in our case, this is usually a read from the original code segment, which is caused mostly by indirect branch instructions or jump tables, as we'll see later. The second case, where the instruction pointer and the faulting address are the same, means that control was transferred to a piece of memory that is not allowed to execute any memory. And again, in our case, this corresponds to control transfers to the original code segment, which is mostly due to function pointers that have absolute addresses. So let's start by seeing how we handle jump tables. So on the top, we see an example for a jump instruction that is generated as part of a jump table, which is the translation of a switch table in C. As we see here, when this instruction is going to be executed, we will get a trap because it accesses locations in the original code segment. And based on that trap, we'll have the instruction pointer, which is the address ending on CE, and also the faulting address, which will be some address within this table, these 4 words down there. So what we'll do is we'll start by the faulting address, and then we will scan before and after to find any relocatable offsets, which is these absolute addresses. And then finally, we will also fix the absolute address within the instruction itself. Now, in the second case, where the instruction pointer and the faulting address are the same, which, as I said before, this corresponds to cases where control was transferred to the original code segment, what we do is we start by searching all the code segment and the initialized data for this specific value of the faulting address. Now, if we find only a single hit, we assume that this was the relocatable offset that caused the trap, and then we go ahead and fix it, and also reconstruct the relocation info for that. In case that we have more than one result, then for every result in the initialized data that could correspond to a pointer value, which could be part of an array or a structure or anything, we will try to verify that this is the case by checking whether there is a reference to that. So for example, if, assuming that we have a statically initialized variable with a function pointer, we would need to have a reference from somewhere in the code to that variable in order to verify that this is the case. On the other hand, for any hits we find in the code segment, we will try to verify whether it does belong to an instruction, probably as an operand, and then again go ahead and fix it and reconstruct the location information. Now, even after we discover and fix a relocatable pointer, there could still be copies of that, of its original value in dynamic data, like in stack or heap. And this means that we might get more traps for the same pointer later on, even though we have fixed it already. So normally, this would be okay after we restart the program, because we will, at this time, we'll have the relocation information, and we will fix it as soon as the programs get loaded. So every copy in the dynamic data will be fixed. But until we do so, we will be getting more and more exceptions for the same values. So in our case, as an optimization, we try to find simple cases where these copies are being performed to dynamic data and try to fix it in place in order to avoid the performance penalty. And these three instructions here have an easy example of that. So we see that there are simply copy instructions copying a pointer value to a global memory location. So for these cases, we can go ahead and then change the memory, the copy of the original pointer value within the global memory. Now, finally, when something falls out of the rules I described before, we generally flag it as a code reuse attack. So more precisely, we detect an attack if we can't find a corresponding code pointer for the folding address, or we cannot verify that the folding address is a legitimate pointer based on the rules I described before. This, as you can see, allows for a limited reuse of legitimate code pointer targets. For example, every function entry or jump table targets. However, when these have not been reconstructed yet, because after the first run, when we find the missing relocation information and we are able to successfully relocate it, we do not allow the reuse of these paths anymore. So as I said, this is only a very limited set of gadgets which quickly syncs over time as we discover more and more locations while the program runs. So for the implementation, we developed a prototype on Windows XP, which still works on Windows, on the latest version of Windows 8.1, because for the APIs we used, there was no big changes. And most of the implementation is based on the Windows debugging API, which is a two-process API, the parent being the debugger and the child process being the debugged one. All the reconstruction logic is on the parent process, which is responsible for spawning the child process, the one we want to reconstruct the relocations for, and then also handle any debug events that originated from the child process. For example, all the memory access violations, loading of external DLL libraries, and so on. And then for the evaluation, we had a two-part evaluation. First part, we wanted to evaluate the performance overhead of reconstructing this missing information. And for that reason, we used the Spec 2006 benchmark suite, and we compiled all the benchmarks without any relocation information. And then we tried to measure the slowdown of applying our technique to reconstruct this missing information. In addition, we also did some use cases with real applications, like old versions of Internet Explorer and Adobe Reader that were missing this information. We tried to see whether we were able to successfully reconstruct it. So let me start by showing some statistics before the performance results. So here, for each of the benchmarks in the Spec 2006 suite, we see on the first column the possible pointers we're able to find. So this is an initialization step. When we load the binary, we go through all the code and initialized data, and we try to find values that fall within the code segment that could be potentially be absolute pointers. And then on the second column, we see the number of jump tables we were able to reconstruct when we executed these programs, followed by the number of verified pointers based on the technique I described before. And then we also have the percentage of times that these pointers were verified because they only have a single hit, followed by the number of times we got a trap for a copy of a pointer due to dynamic data. And then the next column shows the number of times that we were able to perform the global optimization I described before. And finally, of course, the number of relocations we were able to reconstruct at the end. So two things that are important to see from here is that the single hit ratio is relatively high most of the times, which makes verification easier for us. And also another interesting thing to see is that the number of times that we get a hit for an address that we have already fixed due to dynamic data, it has a high variance. So it's really based on the program behavior. And we see that this ranges from a few tens to tens of millions. And as we'll see in the next slide, this is usually the main cause for the performance slowdown we see. So here's the first results for the slowdown. What we did is that we executed all the benchmarks to get the baseline by loading them to their preferred location. So even though they didn't have relocation information, they would work just fine there. And then we did a second run by using our technique, which was the discovery run. So as I said before, we changed the text to a new random location and tried to find all the missing locations by monitoring the access violations. And this, as we see, had a relatively large overhead in some cases, mostly on GCC and Perl, which again, as I showed you here, was mostly because of the number of times of copies of pointers that were reappearing from dynamic data. But what's important to see here was that the second time we executed each of these benchmarks, there was no performance overhead, because in the discovery round we had found all of the relocation information, and by reconstructing it, we were able to fix this at load time. So nothing else, had to be performed at runtime. So although the performance penalty only appears, in the first run, the discovery one, as I said before, we still wanted to see whether we could do any better. And one strategy to do so was to try to discover and reconstruct this misinformation incrementally. And one way to do that was by executing the programs with with increasing loads. So we started with a small data set, and then we go further with larger ones. So luckily for us, the spec suite comes with 3 workloads, the test, train, and the reference one, which are of increasing size. So what we did was to first execute all the programs with the smallest workload, and then discover the relocation based on that, and then use any discovered locations while running the program with the next workload, the bigger one, and so on until we get to the third one. So here, although we see that for example, for the GCC case, that was the worst one before, that the first run is even worse than before, it's 16 times slower. Overall, when we compare the reference one, we see that it's 6 times faster than before. Because here, although it was less than 8 times slower, the amount of time was much more at the end. So for the use cases, as I said in the beginning, we used a couple of real-world applications, and these were Internet Explorer and Adobe Reader. Both of them had locations stripped from the executable files, and this used to be the default policy up to some version of Visual Studio, because the .exe file is the first file loaded, so there was it was always guaranteed that the address it wanted to be loaded will always be free, so locations were stripped for that reason. And after executing them both with our prototype, we were able to successfully reconstruct all the missing relocation information. So to summarize, we introduced a technique to dynamically reconstruct the missing location information, which allow us to enable ASLR on binaries that were missing that info. And we developed a prototype for Windows. And based on that, we were able to experimentally evaluate the performance. And also we applied on real-world applications to see whether it runs. So thank you. I'm taking questions.
Questions? Thanks, Vasilis. Christian.
I have a conceptual problem, I think, with this. What I didn't understand from your talk is, so you have this relocation, which is done during runtime a bit. You know, you have this old text section. And what happens if the attacker is now trying to reuse code which was in the old former text section? Wouldn't you also redirect him to the original, to the new part of the code then?
Well, as I said, this will only happen if it targets one of the, let's say, beginning of a function or a beginning of a target of a switch statement before we have reconstructed the relocation for that. Because, coming back here, if the attacker tries to go to any location that there is no absolute address for that location within the executable module, we will definitely flag it as a code reuse attack right away. And again, there are also some cases that if we also find an absolute pointer, if we cannot verify that this is a pointer, again, we will flag it as a code reuse attack.
Okay, so you just take care of like allowing the function starts and all this stuff. But can you be sure that during your dynamic training and testing, you actually cover all these different code parts that need to be like readdressed? Because I can imagine that there is some weird functions which are normally never called, but during the normal program time, like after a couple of days, they may be called. So is that also like something suspicious then, like a false positive? How would you handle that?
Exactly. So we don't really, the way it's supposed to run, it's not run only once and then discover everything. And so it's supposed to always execute the program under our tool, let's say. So what I showed before in the performance result was repeating the same thing twice. So doing the same computation twice, we were guaranteed that we get all the, we'll use the same, we'll find the same relocations again. But in normal case, we'll run it always under the tool. So if at some point in time something weird happens and we get to a new code path, we'll find this too.
Okay, so you would relocate it and also then allow the call to the function that you haven't seen before?
Yes.
Okay. So, but that also means that the attacker can, in principle, reuse entire functions. That's right. So you only prevent, like, if you jump the middle of the function, but you can actually reuse entire functions.
Yes.
Like
before we find the relocation for that and we know about it. Yes. Because once we know about it and reconstruct it, then we don't allow it anymore.
Okay. Thanks.
Other questions?
Maybe I have some question, yes, so I tried. So from what I understood, you said, yes, you basically answered it with the first question. You said that the tool needs always to be run because you cannot be sure that all code paths get covered when the relocation information is stored. So I guess it's always some kind of trade-off that you have to, because for example, you don't want user processes to rewrite the binary or something like that. So what would it look like in a shared user environment? Then each user has to do their own training with their process, or how could you optimize that?
You mean in cases where they use the same binaries?
Yes, because you don't want one user to rewrite the binary for other users or to write basically code for other users. So
well, that would depend on policy, based on the exact case each time. But both could happen. Users could share the relocation information they find with each other, or couldn't. But that would be, just an option in the policy.
So it might also be an option to make some kind of trade-off, that you might make some training from a trusted user, store that information persistently, and then still use the monitor, but then you have less training that's done per user, basically.
Yeah, that would be another option. Although, I mean, I cannot think of anything bad happening by having wrong relocation information. But yeah, I'm not sure, you need a lot of trust for that. But definitely,
Yes.
it would be better.
Yes. Okay. Thank you.
Question? So that's good, we have these two, but I have a question, just since I have to. So,
Thank you. So first of all, I was wondering, does that always work, or have you encountered a case where you have, you had problems doing it, or is it always working?
So we haven't proved it works always, but for the cases we tested it, it was working just fine. Yeah.
And so you also said the ones you have looked at that they had removed the location information because this was the default policy.
Mm-hmm.
So I guess this isn't anymore. This is why-
Yes, this is
So do you see this technique to become obsolete, very quickly because there is no need for it anymore, or is there a reason for this to still remain relevant even in a couple of years from now?
Well, it will remain relevant as long as there is legacy software, and most of the cases, software isn't updated as quickly as everybody would want. And there are examples of that, even with the old version of Windows XP, Microsoft trying to obsolete it, and then companies, even financial companies, denying to do so because they were using it even in ATMs or stuff like that. So I guess there's still a need for this type of tools.
Thank you very much. One more question? No? So let's thank the speaker again.